Hello, and once again, welcome to a fascinating popular science topic meant for high school level 9, 10, 11 students, even 12 students can also enjoy this video. And the topic of this program is the semiconductors, the science behind semiconductors, and solar cells. It is going to be very, very interesting, and I assure you, you have to watch till the end. And the part 1 is on semiconductors. Part 2 will be on solar cells. Let's start. Now, needless to tell you, if you are a 9th class student, electrical conductors are the ones which can carry current, and you can find some load, a bulb glowing, a fan, rotating, and all the electrical loads can be applied when there is an electric wire or a conducting wire is there connected to a supplier of voltage. So these are conductors which are having conductivity higher, and in the proper unit it is more than 100 Simon meter inverse. Forget about Simon meter inverse. This is a unit of conductivity which you will learn in a higher level. If it exceeds 100 or 10 to the power positive 2, then we brand that as conductors. And it is the free electrons present in that conductor which are responsible for conduction. All metals, even non-metals like graphite, which is one allotrope of carbon, is also a conductor. All electrolytic solution, sodium chloride solution, or even molten sodium chloride connected to a battery, carrying out electrolysis. In the electrolyte, the ions are responsible for conduction. And the opposite category, which almost do not conduct electricity, are insulators like plastics, rubber, glass, paper, ceramics, china clay, and so on and so forth. They almost do not conduct electricity, and their conductivity range is below 10 to the power negative 11 Simon meter inverse. Now, in between these two categories, the conductors means good conductors, and insulators, the poor conductors. In between them, there is another conductor having intermediate conductivity. They are called semiconductors. These have conductivity lying within the range 10 to the power negative 6 to 10 to the power positive 5, a wide range which we can control. We will discuss how we can manipulate and control the conductivity to lie within the intermediate range, and also to our requirement what particular conductivity you want. The examples are elemental, silicon or germanium. These are the two important and widely used elemental or elementary semiconducting material, and binary semiconducting material is a compound between two elements, gallium arsenide, indium stibide. We'll talk about that later. All computers, mobile phones, TVs, and all the hosts of electronics devices, they are made up of these semiconductors, either silicon chips, which are easily and abundantly available, or nowadays gallium arsenide, a binary semiconductor. And I've told you that we can control the conductivity for semiconductors. And the most important difference between semiconductors and conductors is that the conductivity increases with increase in temperature for semiconductors, but the opposite happens for conductors. If you increase the temperature, the conductivity will decrease due to increase in the resistance. The flow of electrons get resisted by the atoms because the kinetic energy of the electrons, moving electrons, get increased. And so also the amplitude of vibration of the seeding atoms at their mean positions also increase. So they hit on each other and the flow of electron gets slowed down. So the conductivity decreases with increase in temperature for conductors. But opposite thing happens, such resistance is not there at the level of semiconductors. So if you increase the temperature, the free electrons which were not free will become free and conduct to a moderate extent. Right? Is it going well? Now these are the three examples. One, conductor, copper wire, for example, inside the insulation, and here the PVC coating outside the conductor. This coating is completely insulator, and in between you find silicon chips. These are the silicon layers which are been pasted over one another. These are semiconductors. And our common pencil, as we say pencil lead, is actually not lead. It is graphite, one of the allotropes of carbon, which is a good conductor. And even the electrolytes, where we conduct electrolysis, molten sodium chloride, for example, here the carriers of charge current is the ions. But in the external circuit, this is the conducting wire, the conductor, metallic conductor. The carriers of carriers of charge or current is electrons, right? Now these are the tables which show how more conducting a metal is. These are different metals. The highest has been for silver, the lowest is for mercury, and carbon, that is graphite, is 100 times less, and electrolytes are very, very low conductivity. Of course they are conductors, but their range is within 10 or within 100, within 10 or 100. And you find germanium and silicon fall into the intermediate type, right? 1 to 10 to 10 to the minus 4 usually. And these are the materials which have almost no conductivity, insulators. Now here you find opposite trend of temperature rise with conductivity. For conductors it decreases, and for semiconductors it increases. So also insulators, but we don't get any benefit. By the time you continue to heat a glass or a plastic, it would melt and the circuit will be open. So there is no practical application of increase in temperature to get some conductivity for insulators, right? Now I'm showing you a very beautiful video which was recorded in MITK, and I really salute to the instructor who has done this. We'll see only 50 seconds from the start. Now see, he'll be putting the two electrodes on a metal and the light glows. It's a conductor. He'll put between a bottle, glass bottle, and the light will not glow. And he will do the same thing with a silicon chip or silicon wafer. He will not find the light glowing at ordinary condition, but when he heats it at a higher temperature, it will start glowing. Then when it cools, it will again, light will go down, will go off. Only when at higher temperature it glows, it conducts. Already I have told you there are two types of semiconductors. It can be either elementary, made up of a single element like silicon or germanium. But if these pure semiconductors, which will act as an insulator at room temperature, is mixed with some impurity, then that become a conducting material and becomes a semiconductor at room temperature. Its conductivity is risen manifold, but they don't become conductors. They remain in the semiconducting range, but at room temperature they start conducting electricity. No need to heat as you found a little earlier. So this mixing of impurities is called doping, and the substance which is mixed, the impurities, they're called dopants. Doping and dopants. And there is another type of semiconductor that is called binary semiconductors, which is a compound between two elements. One from group 13, you can see group 13, boron, aluminum, gallium, indium, thallium, and the other from group 15, nitrogen. First, nitrogen usually is not used, phosphorus, arsenic, antimony. So this binary compounds like gallium arsenide, indium stibide, aluminum phosphide, this is one category. And the other category is by mixing, and not mixing, by making a compound. I'm not talking of doping. I'm making a compound between group 12 element, zinc, cadmium, mercury, and another element from group 16, 12, 16, 13, 15. 12, 16, we choose either sulfur, selenium, tellurium. These are the three chosen, not oxygen. So zinc sulfide, cadmium sulfide, cadmium selenide, mercury telluride. These are another category of binary electrolytes, binary semiconductors. We call this type, we call it 13, 15. This name has got 13, 15 type of semiconductors, and this we call 12, 16 type of binary semiconductors. But this semiconductor is also to be doped, added with impurities if you want to get conducting property at room temperature. Doping is inevitable, whether it is a single element, elementary semiconductor, or a binary semiconductor. Now let's see. The type of doping classifies the semiconductors into two types, N-type or P-type. And let's see what is N-type semiconductors. When the virgin elementary semiconductor like silicon or germanium, the pure silicon or pure germanium is doped. Don't confuse doped with binary. Doped is mixed with a little, I repeat, a little impurities from group 15, either phosphorus or arsenic or antimony. It is mixed or doped. These are called pentavalent impurities. Then we get this N-type semiconductors. Now what happens? What happens, I show you. This is the structure of, say, silicon. It's exactly diamond-like structure. Each silicon is covalently bonded with 4 other silicon atoms, describing a gigantic network. No silicon atom is idle, and it has used all the 4 valence electrons because it belongs to group 14, where its younger sibling sits above it, carbon. So valency 4, all the valence electrons are used, and the silicon structure is a gigantic network. And I'm showing, to simplify, I'm showing in a planar model where you dope, for example, the impurity is group 15, and we select phosphorus. We can also select arsenic, also select antimony. And in doping a small quantity of phosphorus with virgin silicon, what happens? Some of the silicon sites or places are replaced by phosphorus. So in the places of silicon, some phosphorus atoms sit. For example, in this was previously a silicon, but when phosphorus has been doped, this place has been now occupied by phosphorus atom. Now what's the difference? Phosphorus has 5 valence electrons because it belongs to group 15. So after bonding with 4 electrons to the adjoining 4 silicon atoms, 1, 2, 3, 4. What happens to the silicon atoms are satisfying their valency, but what happens to the extra 5th electron of each doped phosphorus atom. It remains free. So these constitute a bunch of free electrons from those phosphorus which are sitting at the silicon places. So these free electrons make it more conducting, but not so more that it will be branded as a conductor, to the extent that you can use favorably for an electronics device. Now same thing I have shown, that each phosphorus atoms now is left with an extra unutilized free electron to conduct electricity, because phosphorus needs only 4 electrons to bond with the adjacent 4 silicon atoms, right? Now this we have already discussed. So the current carrier, the charge carrier of this N type of semiconductors is mostly free electrons. We have already discussed that. Why we call it N type? Because the conduction takes place by free electrons which are negatively charged. So N stands for the N type of semiconductors, negatively charged electrons at the heroes to conduct electricity. Of course, let me tell you that every type of semiconductor, you have both two types of carriers, charge carriers, electrons and holes. We talk about holes after a bit, just hold on. And these impurities are called pentavalent impurities. They are also called donor atoms because they donate free electrons to conduct electricity. Therefore, they are called donor atoms. Now, let's talk about P-type of semiconductor. In P-type, we dope a virgin silicon, a pure virgin silicon or germanium with a trivalent group 13 impurity. Just like we have a saying in advertisement of some detergent powder, daag achhe hain. Daag means impurities, or impurities are good, so that if our shirts or our clothes are dirty, then we can use detergents more and more, wash it, clean it, snow white. So daag achhe hain, that is being utilized here. In semiconductors, impurities are inevitably needed to enhance its conductivity to the semiconductivity range and utilize it in the way we need. So when we do dope either boron or aluminium or gallium or indium belonging to group 13, then we get this type of conductor known as P-type. I'll tell you why they are called P-type. Now what happens, if you see the structure of silicon, and this is shown in a 2D mode, that each silicon is bonded with 4 other silicon atoms. But once you dope a little bit of boron, then some of these silicon atoms are replaced by boron atoms. Ironically, interestingly, boron has only 3 valence electrons to bond fully with 3 neighboring silicon atoms. But what happens to the 4th place? The 4th place is vacant. But the other silicon, adjacent silicon, has 1 electron. So that electron is not a free electron. It is sitting tight to the silicon nucleus. So it's not moving at all. Silicon is binding that electron. But what happens to the hole? So this vacant space is called a hole. So remember, this important word in semiconductor technology or semiconductor science is the hole. So hole is created at every boron atom. Every boron atom. The corresponding electron is there in the silicon atom, but that is being tightly bound. These holes are the heroes here. So the conducting materials, the charge carriers here are holes. I'll tell you how holes are the heroes here. Now see. What happens? A neighboring bond pair loses 1 electron so that the hole is occupied. A new hole is created here. Once you apply a potential difference across this type of P-type of semiconductor, then what happens? The electron from a bond, from a normal covalent bond, slips to the adjacent hole and a new hole is created. and another electron from adjacent bond slips and takes its place, occupies the position of the hole, and a new hole is created in the left. So hole migrates in one direction. For example, say leftwards, new holes are created, not the same hole. And the electron hops from one position, one bond to the hole. Then one bond to the hole. So electron hops. This electron is here, the other electron is here, new hole is created here, the other electron is here. So electron virtually does not move from one place to the end point of the electrode and conducts electricity. No, electron gets trapped inside the hole. So electron is not taken as the charge carriers. Instead, a hole, not a newly created holes are taken to be the charge carriers which are mobile. The holes migrate. Of course, there is nothing. Hole is an empty space, but they are called positive holes. They are electron holes, but they are treated as positively charged entities, hypothetically positively charged quantities. They are electron holes, the absence of electron, but they are called positively charged particles. They are free. The holes are free to move, but the electrons are not free to move. Therefore, the impurity boron aluminum from group 13, they are called acceptor atoms because they have holes to accept electron from the other bond. Right? Now, I am showing you here, and the conventional direction of current is in the external circuit, it is the opposite of the flow of electron. And in the p-type of semiconductor, it is the direction of the hole migration. Hole is as if it is a positive charge, right? So the direction of the hole migration is taken to be the direction of current inside the p-type of semiconductor. But outside, there is no hole. This is a conductor where the free electrons are involved in conducting electricity. Now, why it is called p-type? Because the positively charged particles, these are held. The holes are held as if they are positively charged particles. Hence, they are called P, positively charged. So, p-type of semiconductors. Not that these holes are truly protons. Instead, the vacant space created by the disappearance of electrons. The hole behaves as an apparent free particle. Apparent free particle with effective positive charge. Effective, not true. Because the hole is exposed to the nucleus, which carries positive charge. So in all imagination, we can take it as positive charge, though really not positive. So the majority charge carrier, current carrier inside a p-type of semiconductor is holes. Holes, the number of holes will be much greater than the number of free electrons in p-type. But in n-type, it is the opposite. Number of holes is insignificantly lower than the number of free electrons in the n-type of semiconductor. Now, the important thing, the doping amount is extremely small. Can you imagine? It will be as small as 1 to 10 ppb, parts per billion. In every 10 to the power 9 gram of the semiconducting material, you only need to mix 1 to 10 parts, or 1 to 10 grams. So not that you are making a binary compound, 1:1 basis. No. In 10 to the power 9 parts, you are adding 1, 2, 3, depending on your requirement. And I have already told that in each type, n-type or p-type, the carriers are always both electrons and free holes. Free electrons and free holes. But in n-type, the number of free electrons is much more than the number of holes they migrate. And in case of p-type, the number of holes is much greater than the number of free electrons. So the real hero in p-type is the migration of holes, and the real hero in the n-type, migration of electrons, free electrons. Now therefore, we have two terms, intrinsic and extrinsic. Intrinsic semiconductor is the one which is pure. not doped, undoped, like pure silicon, pure germanium, pure gallium sulfide. That is, I will talk about that later. Pure. But if it is doped with impurity, it is called extrinsic semiconductors. Extrinsic semiconductors are semiconductors at room temperature, right? No need to heat. So the same p-type having hole in each boron or aluminum or gallium, group 3 impurity, group 13 impurity, and this is n-type semiconductor where there is a free electron with each arsenic or any 15 element atom. Now we will talk about the band gap model, the band theory, the energy gap or band model of electrical conduction. This is a very important tool given by both chemists and physicists to understand what happens. I am not going to the details how the orbitals are formed, but see, in a crystal, metallic crystal, for example, sodium metal or iron metal, a lot of hundreds and thousands of atoms, very close, tightly, sitting opposed to each other, close to each other. I mean, they are touching each other. So as a result, the orbitals, the valence orbitals, they combine in a manner two big orbitals. They are called molecular orbitals are formed. One is called a valence band, having lower energy, where the valence electrons of all the atoms, they sit, they move, but they do not conduct electricity. And the other one having higher energy is called the conduction band. So wherever you go, you will only hear two terms: valence band, conduction band, valence band, conduction band. Any electronics person or semiconductor physics person, he will be telling you time and again valence band, conduction band. So I am sounding you these two popular terms in semiconductor technology. So valence band is the molecular orbital of collective molecular orbital of all the atoms, where the valence electrons of all the atoms, they remain, but they are not capable to conduct electricity once you apply the potential difference. Once they are promoted, they are excited, they are pulled to the conduction band, which is of higher energy, then only they can conduct electricity. They are then called free electrons. But when they are sitting at the valence band, they are sitting tight. They are not free to move. They are sitting tight. Once they are promoted to the higher energy conduction band, they become free, and you can just apply a PD which will flow in a particular direction. So the conduction band is also called LUMO, lowest unoccupied molecular orbital, and the valence band is called HOMO, highest occupied molecular orbital. And the difference between them is called the band gap. The energy difference between the valence band and conduction band is called band gap, which is very high, greater than 10 electron volt. Here the energy is measured in electron volt unit. Forget about these energy terms. So if it is exceeding 10 electron volt, the gap is more, then nothing will happen. The electron cannot jump to a higher energy level. On large heating, the very high temperature, the the insulator will totally break down, melt, and there will be no circuit. So due to high band gap in insulators, electron cannot go to the conduction band. But in conductors, the band gap is nearly zero, almost no band gap. So even at room temperature, thousands and thousands of electrons are there in the conduction band. They are free electrons. Just to apply the PD, and they drift in a particular direction and initiate current. And interestingly, at absolute zero Kelvin or minus 273.15 degrees Celsius, all the electrons are in the conduction band. All. You will be astonished why at 0K minus 273 degrees Celsius, all the electrons are in conduction band. At that time, you can tell a metal to be a superconductor. Superconductivity is another fascinating topic, and I will be making my next stage video after this and solar cell. My next stage video will be a school level superconductivity, how you can achieve superconductivity at 0K. Every metal will be a superconductor, but no use. You can't achieve 0K or so small temperature. You have to have superconductor at a higher temperature. We'll talk about that later. So for conductors, there is no band gap, but for semiconductors, the band gap is small. In the vicinity of 1, 2, 3, max 5. So this gap can be surmounted, not raising the temperature to such a high level. By just raising the temperature, some electrons will gain energy and jump to the conduction band and conduct electricity. Or if you want to dope, then this band gap is further lowered. So much so that electrons can easily, just by applying a PD, it will jump. The energy requirement for jumping becomes very little at room temperature and you get semiconductivity. Now I am showing you this video from 1.5 seconds, the same instructor. And in insulators, the band gap is high. The electrons in the valence band cannot jump to that extent to surmount a large barrier. For example, glass doesn't conduct. But in conductors, the band gap is absent, it is 0. So many electrons are already there in the conduction band. But in semiconductors, this gap is neither high like, this is about the insulators which can conduct electricity at a very high temperature, but by that time it will break down and the circuit will be open. But in case of semiconductors, for example, silicon, the band gap is moderate, small, to the extent that by hitting mildly, not to a very high temperature, the electron will jump. Thank you, MIT K12 videos series. Now, I have already told this thing, and superconductivity, I will not talk much about it. I told you. But one thing I'll say, that at 0 Kelvin, minus 273 degrees Celsius, all the electrons in a conductor come to the conduction band and make it a superconductor. But as you continue to raise the temperature, the kinetic energy becomes more and more, both for the electrons and the vibrating atom sitting at the mean position. Then the resistance factor comes in. Due to increase in the resistance, more and more electrons can revert back, come back to the valence band, and fewer electrons remain in the conduction band. So number of free electrons get reduced because of increasing resistance, and the conductivity is reduced. But not the same case with semiconductors. Semiconductors at 0K, remember at 0K, all the electrons are in the conduction band. Valence band. No electron in the conduction band. So the resistance factor is not a factor here. When you heat it, then electrons can go to the conduction band and conduct electricity. So therefore, for certain range of temperature, the conductivity increases with increase in temperature. But if you can dope it with a proper dopant, then the band gap will be reduced and the conductivity will happen without raising the temperature, even at room temperature. So I have already explained that in this case, what happens when you dope and prepare N-type, then the new band is created, new band. Besides valence band and conduction band, a new band is created due to the presence of these extra free electrons from each phosphorus or arsenic or antimony. So they form another energy band called Fermi level, very near to the conduction band. So very easily, even at room temperature, applying a PD, they will jump without any effort. It will jump because the energy gap is very, very small. So they conduct electricity. Similarly, for P-type, interesting thing happens. You might not be knowing this thing. Please hear very carefully. In p-type, due to the presence of a large number of holes for each boron atom or gallium atom doped, you will find, the holes, they produce another Fermi level which is close to the valence band. The free electrons Fermi level was close to conduction band for n-type, but for p-type, the holes, they create another energy level nearer to the valence band, so that one electron from the valence band will just easily come to occupy the whole Fermi level, and a new hole is created in the valence band. So the whole migration and conduction of electricity occurs in the valence band. A new hole is created here, electrons from the adjacent bond position comes here, and another hole is created here. So the hole migrates in this direction, and electron doesn't migrate, it hops and occupies the position of the hole. So the irony is the conduction of p-type of semiconductors is in the valence band, right? So these are the examples where I have shown you the band gap. All of the semiconductors lie within 5. Once it is more than 5, even diamond is an insulator. And aluminum nitride, a binary compound, is also an insulator, not a semiconductor. Now, how to dope a binary semiconductor? That's very interesting. Since I will be closing after a bit, do not forget to watch till the end. Another 2 to 3 minutes I will take. So we have discussed how to dope a virgin elementary semiconductor like silicon or germanium. But if you have a binary semiconductor prepared, as we call 13-15 or 12-16 type of semiconductor, 1:1 ratio. So that has to be doped also, but the dopant is in this case silicon. Silicon was the hero, the main person, and gallium or arsenic was the dopant, as the case may be for getting P and N type of semiconductor. But here in gallium arsenide type of virgin semiconductor, the dopant is silicon to give both N type and P type. Some different valence atom has to be given, because gallium and arsenic, they belong to two different groups, and you have prepared a binary compound. But for doping, you need to have another group element. Silicon is the best choice for doping. Let's see how we dope. Now, gallium arsenide structure is very typical, similar structure to silicon. Each gallium is bonded to 4 arsenic atoms, and each arsenic atom is also bonded to 4 gallium atoms. You will be surprised how. Gallium has 3 valence electrons and arsenic has 5 valence electrons. How it is possible? That is possible by 3 normal bonds from gallium and another dative or coordinate covalent bond from arsenic, because the 4th and 5th electron, it is in the form of a lone pair. So that pair is now a bond contributed or donated by one atom, which is arsenic. So this is a coordinate covalent bond or a dative bond. Therefore, every gallium is bonded to 4 arsenic atoms, and each arsenic atom is also bonded to 4 gallium atoms. Now what happens when you dope a little bit of silicon at a higher temperature greater than 900 degrees Celsius? These doped silicon atoms, they take some of the places, displace some gallium atoms, group 13 gallium atoms, and take their places. Who takes whose place? Silicon takes the place of gallium. In gallium arsenide, some gallium goes and in its place silicon sits. Now silicon has an extra electron. We needed only 3 electrons for the bond. So silicon has 1 extra electron. So what will happen? That becomes free. So the N type of semiconductor is formed when you dope silicon to gallium arsenide at a higher temperature greater than 900. Now the real donor is not silicon. Silicon is, out of the 2 electrons of arsenic, 1 electron comes and joins with silicon to form a normal covalent bond, and the real donor atom is now arsenic. Later that has a vacant d orbital to carry at a higher energy level to make it free. So although we call silicon here is the donor atom, It carries the extra electron for conduction, but the real donor atom is arsenic. The silicon arsenic bond is now normal. Similarly, if you dope gallium arsenide with same silicon at a lower temperature, less than 700, at that temperature condition, some of the silicon atoms displace arsenic group 15 partner and occupy their positions. Once arsenic is gone, 5 electrons gone, and you have 4 electrons, so a hole is created. 5 electrons gone, 5 electrons wala is gone, and 4 electrons wala has come, so there is a hole. But the real hole carrier is not silicon. Again, the gallium being the group 13 element, now carries the hole. Silicon, binds, because it has valency 4, it will tightly bind its electron, it will not allow to go easily, but the real hole carrier is gallium. The acceptor atom, though we call silicon is an acceptor here in p-type. This is p-type semiconductor. That was when doped at higher temperature, it was n-type, and when doped at lower temperature, it is p-type. So a hole is created, a positive, it's called electron hole, but it is positively charged. Imagination. So a p-type semiconductor is formed when we dope silicon at a lower temperature. It takes the position of arsenic, but the real hole comes to gallium, right? Where the silicon, that unpaired electron is tightly bound to silicon, and the hole comes. So in this way, we have, this is this two-dimensional view structure of gallium arsenide. I have not doped. Gallium is black and arsenic is white. So if you dope silicon at higher temperature, gallium will be replaced by silicon, some of the gallium atoms, and produce n-type. And when you dope at a lower temperature, below 700, some of the arsenic atoms will be replaced by silicon. You will be having holes. Bye-bye. How did you like? If you liked it, please do not forget to hit the like button and put a comment. You are very, very miser in giving comments, right? At one line comment when you liked it. But the next video will be still more interesting. Is the solar cell, how the solar cell functions. And if you have not subscribed to my channel, please subscribe. It's not costing either you money or I am getting any money, but we complement each other, encourage each other. Bye bye. See you in the next video. I will be recording just now.